So now we're gonna get to the final type of annuity, or at least the final type of annuity that we're going to learn to model in Excel. So before we get to this, I want to just emphasize something with you guys first, and that is the two types of annuities that are left of what you've done in the A211 curriculum that we haven't covered in this video yet are, or at least in a general sense, are an increasing annuity, which is increasing discretely. So I'm gonna write it down here. And annuity increasing discretely. Uh, Highlight that, put that in bold. And an annuity increasing continuously. Mm, Again, highlight that in bold. Okay, so now I want to quickly explain or get to the differences between these two annuities. The first one is an annuity increasing continuously. We are just going to minus the fact that I misspelled increasing, even though I am a university student and should probably know how to spell this properly by now. So we have an annuity, an increasing annuity, but it's increasing discretely. This type of annuity, so I should say, what I should have said is a continuously increasing annuity. So a continuously increasing annuity, increasing discretely. So this is a continuous annuity where it's an increasing annuity payable continuously throughout the year. Present value of increasing payment. So what happens is that you have a continuous payment stream each year. But at the end of each year, that payment stream increases at the discrete increments. So from time zero to time one, you have continuous payment stream, and then at time one, it jumps up. And then you have a continuous payment stream from the beginning of time two to the end of time two. At the end of time two, it jumps up. Then you have a continuous payment stream from the beginning of time three to the end of time three. So it's a step function. This is called a continuously increasing annuity, a continuous annuity increasing discretely. Because although the payments are received continuously, the increase in the payments occurs discretely or at the discrete time points. We can model this in Excel because what we can do is that we can use the formula for an annuity payable continuously in a year. So this right here, this continuous payment stream is just equivalent to A bar one. And A bar one, which is the continuous an annuity payable continuously in 1 year. It will take this continuous payment stream and make it a cash flow at time zero. It will give us the present value at time zero, because it takes it back 1 year. So it will take this continuous payment stream, give us a value, the present value at time zero, and it will take this one and give us a present value at time zero. What ends up happening is we will have let's see if this thing allows me to draw. uh, I'm too lazy for that anyway. Oh, it does allow me to draw. So what ends up happening is that, let me use a different color. What ends up happening is that this continuous payment stream, when we multiply it by A bar one, or when we apply the continuously payable annuity to it, it will give us a value at time zero, the present value. So we'll have the value at time zero. And this one, because it only does this for 1 year, it won't do it for 2 years. So A bar one will give us the value of this continuous payment stream at time one. And A bar 1 will give us the value of this continuous payment stream at time 2. So what ends up happening is that we have the present values of the continuous payment streams, and we'll end up having discrete payments, which are the dots here, the discrete payments at each time, which we can model in Excel. So this type of annuity, a continuous annuity increasing discretely, we can model in Excel. But then we have this type of annuity on the other side here. Just take out this drawing thing. I don't want to draw anymore. Okay. Then we have this type of annuity, a continuous annuity which increases continuously. So this is the present value of a continuously increasing annuity certain continuously throughout the year. This increases continuously. So we can't apply a bar one to it, because it's not a step function. It's a continuous payment stream that's increasing continuously throughout the year. What would happen for us to model this in Excel? I'm gonna draw again. I'm really getting into this art thing. I don't know why. I'm just discovering this drawing function here, and it's my first time using it, and it's very exciting. In order for us to model in Excel, what we usually do, like we did in the previous example, is that we model discrete payments. So if we had a payment here, for example, if we had a payment here, we had a payment here at each of the different times, we just apply the discounting factor to it to take it back to time zero. Apply discounting factor, take it back to time zero. But here we don't have discrete payments. So what would happen is that we'd have to apply a V factor at each and every T. And there's infinitesimally many T's between any interval here, even from 0 to 1, from 0 to 0, 0,5. And as you can see, there is not infinitesimally many cells in Excel, because what would happen is that we would have to have t equals to 0,0000001, 0,00002, and it'll be like a very, very small number. But there's only so many cells in Excel. Excel is discrete in nature, it's not continuous. So we can't model this annuity. So you'll never get this annuity in A211 or in FinMath. Uh, on the Excel side, that is. I mean, you shouldn't get it. You never know. Maybe the examiners will decide to be creative, but in general, we don't model this in Excel. We model this. So this is the one that we're going to model in this sheet here. So we have a continuously payable cash flow uh, is such that the level rate of payment throughout the year T is this payment for T equals to 1, 2, etc., etc. And you can see that this T increases discretely. At time 1, it's a certain amount, and then when you get to time 2, it increases. Time 3, it increases based on this formula here. So it increases at discrete increments. So we have this right here. So we have a step function, so we can model this. Find the value of the cash flow at time 0 at 10% per annum effective. So first of all, let's note our information. We have our interest rate, which is 10% per annum effective. Okay. Now, how I'm going to note down our payment is that I'm going to have our base payment is going to be 100. Because at in the year 1, we'll have 100 times 1,051 minus 1, which is 0, which is just 100. And then I'm going to have the increase. The increase, I'm misspelling these things. No, not today. The increase is going to be by a factor of 1,05 each year. Okay, because each year we multiply by 1,05. And we're going to need to calculate a bar 1, like I said, in explaining the illustration on the other sheet. So in order to calculate a bar 1, we need delta. And delta is equal to the natural logarithm of 1 plus I. So natural log of 1 plus I. So that is our delta. Let me just see if I calculated correctly. You can use natural logarithms in Excel by just saying ln. Okay, that should be correct. And so our A bar is equal to 1 minus 1 plus I to the power of minus 1, because we want A bar 1 for 1 year over delta. Okay, and so this is our information that we're going to put borders on, and we're going to highlight nicely. Uh, Perhaps you can tell from my very creative use of the highlighter that blue is one of my favorite colors. Okay, so now we draw a timeline. So we have our time 0, 1, up until time 10. And then we have our payments. Now, I want us to note something here. When here I have 0 and I have 1 and I have 2. This is 0 is the beginning of year 1. And this 1 represents the end of year 1 or the beginning of year 2. This 2 represents the end of year 2 or the beginning of year 3. This 3 represents the end of year 3 or the beginning of year 4. So what's going to happen is that here we're going to have 100 times 1,05, and I'm going to fix this 1,05 to the power of 1. I'm going to use 1 because although it says 0, this interval from 0 and 1 is year 1. It's the first year. This interval from 1 to, because this is the beginning of year 1, end of year 1. This is the beginning of year 2, end of year 2, beginning of year 3, end of year 3. So this interval is year 1. So you don't put the payment here, you put it for this interval is year 1. So I'm going to have 1 minus 1. And then we're going to multiply this by a bar 1. And I'm going to fix a bar 1 as well. Because remember, the first portion of this payment, this 100 times 1,05 to the power of 1 minus 1, which is just 100, is received continuously throughout this year. So it's not at time 0 yet. It's received, this initial part of the payment is received continuously from 0 to 1. When we multiply it by A1 or A bar 1, it takes the present value of that continuous stream by 1 year. So it takes it back 1 year, this entire continuous payment stream. So it takes it to time 0. And it's going to do the same thing for the rest of the payments. And so this continuous payment stream, which is received during year 2, so beginning of year 2 up until end of year 2, A bar 1 takes it back to the beginning of year 2. It takes it back by 1 year, which is to the beginning of year 2, which is year 1. And then it does thing here. It's going to take the payment received here. It's going to take it back 1 year, which is here. It's going to take the payment received continuously between this year or during this year, and it's going to take it back here. And that's why in the end, we have a payment structure which looks like it's in advance. What am I doing here? Okay. In the end, it looks like we have a payment structure that is in advance because the A bar 1 takes a continuous payment stream during any given year and sets it back 1 year. And so now because we've converted from continuous payments to discrete cash flows at discrete times, we can get our discounting factors as we usually do, and that's simply 1 plus um let me be fancy and say e to the power of minus time times delta should give me the same thing. This may backfire. Okay, that makes sense because we're at time 0 and these are discounting factors. And then we get our present values for each payment. And again, you can use some product here. I'm going the slow route because I'm interested in seeing the cash flows and how they change over time. And then you get the net present value, which is the sum of all of these. Or alternatively, we can use some product. Ooh, forgot my equals. So when you type in a formula, you always want to put equals, put that equal sign first. And to my first array as the payment, to my second array as the discounting factors, and we get the same answer just as a sanity check. I'm going to calculate the discounting factors here by using 1 plus, just to make sure I'm getting correct things to the minus time. And yeah, it's the exact same values. And so yeah, this is how you model a continuously payable, discretely increasing annuity. That's not what I wanted at all. At all. That's the net present value. And you can verify all of these net present values by calculating it using the formulas that you guys have learned by hand. And how you usually get these questions in FinMath is that you'll get a layered question. So it won't ask you to calculate the present value of an annuity because that's too easy and you are extremely smart. And they're banking on the fact that, that's easy. That's second nature for you. That's easy marks for you. Everyone would get 100% if they just ask you to calculate to do what I've done here, which is the easy part of it. What they're going to ask you to do is they're going to give you a layered question, in which you'll have to apply these annuities to get, the present values, discounted mean terms, payback periods, which you'll learn all in the future. You can get index linked bonds in this. But yeah, since we've covered the basics of annuities, the next couple of videos which I do on Excel will be on applying these annuities. But just familiarize yourself with them in Excel, play around with them, work with a few different examples, a few interesting examples, so that by the time you get like real FinMath questions, because these aren't FinMath questions, these are questions you get in kindergarten or crash. This is play, small play, shallow waters. So by the time you get to the deep waters, you've mastered the small concepts. Okay, see you guys next time. Bye.